Hello, everyone. And this is going to be midterm 3 mastery video key. So the first question is a nomenclature question. It asks us to provide a name for the following compounds. So we'll start with the carboxylic acid. So we want to assign a locant so we can determine the name of the parent. And so we're going to start with the carbon that's part of the carboxylic acid. That's going to be carbon number 1. Carboxylic acids are like aldehydes. They're always at the end of a chain. So this is always carbon number 1. So we don't need to include that in the parent. There is one substituent, which is a 5-methyl group, right? So we would write 5-methyl. And then if this was an alkane, since it's 6 carbons, we would write hexane, but it becomes hexanoic acid. So we add, you can think of, right, starting with hexane, dropping the E and add the oic space acid, right? That's how we get to the name. So hexanoic acid. And then for an ester, right, we are going to look at what's attached to the oxygen, right? And that's going to come first. So this is an ethyl ester, right? So we're going to write ethyl and then space, right? And it's going to be similar to this, except for we're going to add, instead of oic acid, it becomes O8, right? So you can think of the same idea. It started from hexane, but for an ester, we add O8 instead of oic acid. So this is still ethyl 5-methyl hexanoate. The bottom two are amines, right? So again, we can sort of start from the idea that we have a 6 carbons in our parent, so that would be hexane. And then we're going to drop the E and add the word amine. So it becomes a hexanamine. So putting this all together, we have 5-methyl and then hexanamine. This one has a substituent on the nitrogen. So this is what we call an N-ethyl group. So this actually becomes a second substituent, and it's dealt with differently than with the ester. So we can call, we know we have a 5-methyl, right? And now we have an N-ethyl. And so we alphabetize. So M for methyl, E for ethyl, right? Ethyl comes first alphabetically. So we would do N-ethyl 5-methyl. And then because it's an amine, the parent is the same. So we would just continue with hexanamine. All right, so we'll move on to the next question. Provide the missing reagents. Right, so you might recognize that this is a terminal alkyne. And if we're looking at carbons, we have the 6 carbons in the ring, and then we have 2 outside of the ring. So this has 6 carbons, but only 1 outside of the ring. So we're actually doing a carbon-carbon bond cleavage reaction, right? And we do that through ozonolysis. So for an alkyne, we would use ozone and then just an aqueous workup. So if it was an alkene and we were making aldehydes or ketones, you would see a reducing agent as a second step, right? Zinc or DMS, which stands for dimethyl sulfide. But for alkynes, we just need to do a regular aqueous workup. Okay, the next 3 are all oxidations. So we're either oxidizing the benzylic position all the way from an alkyl group, we're oxidizing a benzylic alcohol, and we're oxidizing a benzaldehyde, right? And either way, the conditions are the same. In order to get to the carboxylic acid, we need to use sodium dichromate, right? So maybe even use a different color here. Na2Cr2O7, H2SO4, and water. So now we know which type of things we can oxidize at the benzylic position, right? We just need to have at least one hydrogen here for it to be able to be oxidized. And we can also oxidize alcohols and aldehydes all the way up to the carboxylic acid, but we need the strongest oxidizing agent, right? So PCC, for example, would not be strong enough because that would stop at the aldehyde stage. We need the more strong oxidizing agent, sodium dichromate. And then lastly here, we have another reaction which is going to add a carbon. So notice we only have the 6 carbons in the ring, right? And now we have 7 because we've added this carbon. So we need to do something where we add a carbon. Because of the fact that the bromine is attached to an sp2 hybridized carbon, we have to use a Grignard. We cannot use sodium cyanide. So we're going to start with magnesium to form the Grignard reagent. We'll add in some dry ice, which is solid CO2. That will form the carboxylate, and then after an acidic workup, we will have the fully protonated carboxylic acid. All right. Moving on to question number 3. Okay, so the question is, how can carboxylic acids be selectively reduced in the presence of a ketone? Would standard reducing agents such as sodium borohydride or lithium aluminum hydride work? Why or why not? So it's important to remember that it's easier to reduce a ketone than a carboxylic acid, right? So these are, the carbon here is more electrophilic, right? So it's easier, this is an easier carbon to reduce, right, than the carboxylic acid. So selectively reducing it is very difficult, right? If we were to use either sodium borohydride or lithium aluminum hydride, we would actually not get the desired product. So let's actually look and see what we would get, right? So sodium borohydride, right, or lithium aluminum hydride. Normally you might see like water or methanol as a solvent mentioned here, and then a second step of water or H3O plus here. I'm just leaving that out just for simplicity, because these are actually reactions that are not going to produce the desired product. Okay, sodium borohydride would reduce only the ketone, right? It's not able to reduce the carboxylic acid because it's a weaker reducing agent. So it's only going to go for the stronger electrophilic carbon, right? Not the weaker electrophilic carbon. So we would actually get the secondary alcohol from the reduction of the ketone, and then you would draw in the carboxylic acid not touched. Lithium aluminum hydride is a stronger reducing agent, and it can actually reduce both ketones and carboxylic acids. So we would end up with something that is fully reduced, right? We would get a secondary alcohol from the ketone and a primary alcohol from the carboxylic acid. So neither of these, right, reactions produce the desired product. Okay, so do not produce desired product. So then what do we need instead in order to do the selective reduction, right? So the conditions for this are boring and THF. And the reason why this works is because the boron coordinates to both oxygens in the carboxylic acid, and that facilitates the hydride delivery. So in the ketone, there's only one oxygen, so the boron isn't able to coordinate in order to reduce. All right, fill in the missing reagents and structures. So we have an unknown reaction, right, to produce some sort of product, but then this product will react with ethanol and pyridine or two equivalents of amine. So these reagents are not strong, right? Just a regular amine, not charged. An alcohol is not charged. So those are considered weaker nucleophiles. So we're going to need a strong electrophile here in order for these to be successful reactions. So we definitely want to produce the acid chloride, right? If we produce the acid chlorides are the most reactive of the carboxylic acid derivatives. So then these other subsequent reactions will be very successful. In order to produce an acid chloride from a carboxylic acid, we need thionyl chloride, SOCl2. And then this is another clue, right? If we treat an acid chloride with just water, right, weak, very weak, this is a strong enough electrophile that it will go back to the carboxylic acid. So from here, right, we can see, okay, well, what would happen then if this acid chloride was reacted with an alcohol with an equivalent of pyridine to act as base? Well, it would produce the ester. It would produce the ethyl ester. So we can go ahead and draw that in. And then two equivalents of amine. One acts as a nucleophile to do the nucleophilic attack, and the other one acts as a base. So it's just easier to use, typically to use two equivalents of this than to add an equivalent of pyridine as base. Just less things to add, right? So one of these equivalents is basically acting as a pyridine substitute and acts as a base. So we're going to make the amide. Right, with an ethyl group here, right? And one of the hydrogens is gone because it gets deprotonated, right, with the other amine. All right, next question. Fill in the missing products. So in this case, all of the reagents are given to us. We just need to fill in the missing products. So let's see, we're starting again from this acid chloride, right? What happens if we react it with lithium trialkoxy aluminum hydride? Well, this is a weaker reducing agent so that this reduction will stop at the aldehyde stage, right? So we want to recognize that those conditions convert a acid chloride directly to an aldehyde, and that this reducing agent does not further reduce the aldehyde. Lithium aluminum hydride would first produce the aldehyde, but it's a very strong reducing agent, so it will further reduce the aldehyde to all the way down to an alcohol. So we'll get benzyl alcohol in this case. Right, if we wanted to, we could treat that alcohol, right, which is primary, with PCC, and it would oxidize back up to an aldehyde. So then that gives us two ways to produce the aldehyde, right? We could go directly, right, with this less reactive reducing agent, or we could do two steps, reduce all the way down to the primary alcohol, and then oxidize back up to the aldehyde stage. Of course, if we treat a primary alcohol under our strong oxidizing conditions, it would oxidize all the way back up to the carboxylic acid. Okay. The next question says, show 3 different reactions. Sorry about this. And not, sometimes just really doesn't want to focus. See if it'll focus on my phone. No. Oh, maybe. Let's see. How about a calculator? There we go. It's better. Okay. So show 3 different reactions to synthesize a methyl ester. 2 reactions will start from a carboxylic acid and 1 will start from an acid chloride. Okay, so we said we will draw 3 reactions, right? 1 could start from a carboxylic acid. We could use any carboxylic acid, but I'm just going to use benzoic acid as an example, right? So I will just draw that twice. Since it said I was going to do 2 reactions from an acid chloride. And leave some space on this one. And it wants me to synthesize a methyl ester, right? So I'm going to go ahead and draw in the product here. I want a methyl attached to that oxygen. And then 1 reaction will start from an acid chloride. So we'll just do an example. We'll just use benzoyl chloride, and we will form an ester from that. Methyl ester directly. Okay. So now we need to think about the reagents. So we want to, 1 way to go to an ester from a carboxylic acid is to deprotonate the acidic proton on the carboxylic acid. Right, recall this has a pKa of about 5, so it's fairly acidic. So we can treat that with sodium hydroxide, and that's a strong enough base to fully deprotonate the carboxylic acid, producing a carboxylate, which can act as a strong nucleophile and do an SN2 reaction with methyl bromide or methyl iodide and produce the methyl ester. The other way is to use the name reaction, right? The Fischer esterification. And that utilizes an alcohol, an acid, and an acid catalyst, right? So because we're making the methyl ester, then we want to use methanol. And then we just need a strong acid catalyst, like a drop of sulfuric acid, and that is usually just written as a proton in brackets. And then from the acid chloride, remember that this is one of the most electrophilic carbons of the carboxylic acid derivatives. So it doesn't need a strong nucleophile to attack there. Even weak nucleophiles, right, attack there. So methanol, right, even a weak methanol nucleophile can attack there directly. We don't need an acid catalyst because this is a much stronger electrophilic carbon than this one is. The point of adding the acid catalyst is it protonates the oxygen and makes a stronger electrophile at this carbon. So we already have a strong electrophile, so we don't need an acid catalyst. Sometimes people will throw in an equivalent of pyridine, though, to act as a base, and that prevents HCl from forming as a byproduct in this reaction. Okay, the next question is a bunch of different reactions with LAH, right? And showing the product after reduction with LAH. So aldehydes, reduce down to a primary alcohol, right, with LAH. Just note that if we have 4 carbons over here, we should have 4 carbons over here. So make sure to always double check that you're not accidentally adding or losing a carbon. LAH can also reduce a carboxylic acid all the way down to a primary alcohol. It will also reduce an acid chloride down to the primary alcohol, and it will reduce an ester down to the primary alcohol. You would also get methanol in this one, but that's just a byproduct, so typically we don't mention it. Right? But both the amide and the nitrile will reduce down to an amine. So that is something to remember, that we would get the primary amine, right, instead of an alcohol with these two. And these are the ones you can see actually have a nitrogen, so it's a good way to remember that. Fill in the missing reagents and structures here. So we have the conversion of an alkyl bromide to an alcohol, right? This is primary, so it's going to undergo a SN2 substitution reaction. So we're going to use a strong nucleophile. So we're going to use sodium hydroxide. From a primary alcohol to a carboxylic acid, this is an oxidation. We're going all the way up to the carboxylic acid, so we need the stronger sodium dichromate. If we treat a carboxylic acid with PBr3 and bromine, and then a water workup, so initially this converts the carboxylic acid to a acid bromide, which then brominates at the alpha position, but the water converts the acid bromide or acyl bromide, right, back to the carboxylic acid. So in the end, the product that we would get is the carboxylic acid with a bromine at the alpha position. And then from here to here, notice that this has 3 carbons, right? It's an alkyl halide with 3 carbons, and then we're producing a carboxylic acid with 4 carbons. So we are adding a carbon. So we actually can do this one of 2 different ways, right? So I'm just going to put an or here, right? Because there's 2 different ways that you could do this. You could do the same reaction we did on an earlier question, which is formation of the Grignard reagent from the alkyl bromide, add CO2, and then do an acidic workup. That would be one way you could do it. Or because it's primary, so we can do an SN2 reaction, we can also use sodium cyanide, and that will actually give us our extra carbon right there. So we'll get a nitrile intermediate, and nitriles can be hydrolyzed to a carboxylic acid under acidic conditions with heating. Okay, what is the product if butanal is treated with sodium hydroxide? And what is the name of this reaction? What if it's treated with sodium hydroxide and also heated? And what is the name of that reaction? So without heat, right, we're going to do what we call an aldol addition reaction. And with heat, we're going to do an aldol condensation reaction, right? And if we think about how to draw the product, the activities showed you a way to do that, right? So we could draw out one equivalent of the bromide and then draw out the other one, right? Sort of the idea would be you could flip this over So 1, 2, 3, 4. Make sure to draw the right number of carbons. We're going to think about forming a bond, right, between the alpha carbon, right, of 1 and what's known as the aldehyde carbon or the ipso carbon here, right? So this is sort of just our thinking process, okay? And then we're going to produce, in the end, a beta hydroxyaldehyde. So we're going to have a bond here, right, between those two carbons. The aldehyde group is going to become an OH, so this will become OH. And then we have 1, 2, 3, so 1, 2, 3. So that would be one way to draw that product. And then a very similar idea here, right? We're going to think of it in the same way, where we're going to imagine these lining up in the same way. But instead of forming the alcohol here, we're going to go all the way to the alkene. Right? So in the end, we will get a alpha beta unsaturated aldehyde. Okay. Show how these two compounds can be prepared from a successful crossed aldol addition reaction. Which one requires LDA and which can you use sodium hydroxide? Okay, so if we think about it, right, and going back to the reagents, I want you to think about the fact that we're going to be, right, making this bond through the aldol addition reaction. So for this one, for example, you could start with the ketone, right? And then we're going to need to use formaldehyde because there are two hydrogens here. And then this becomes, when you break this is going to become a carbon-oxygen double bond, and this hydrogen, which is provided by the workup, won't be there, right? So we're going to end up with this carbon with double bond to oxygen with two hydrogens, so we call that formaldehyde. Because formaldehyde doesn't have any alpha carbons, which can form an enolate, we don't have to worry about that reacting as the enolate. And it's very electrophilic, so it's going to be the best partner for any other aldehyde or ketone. So we can just use sodium hydroxide in that case, right? So we're going to use formaldehyde, draw that in, right? And we can just use sodium hydroxide and it will produce that product via the aldol addition reaction. Okay, moving over here, we have the same ketone being used. So we'll draw that in. The problem is that the coupling partner now, right, is not going to be formaldehyde, right? It's going to be, there's only one hydrogen here. So it will be ethanol. And the problem with ethanol is it has this alpha carbon, which can form an enolate. So if we mixed this and this with sodium hydroxide, some of this will form the enolate from the ketone, and some enolate will form from the aldehyde, which will lead to a mixture of products. So that would not be a successful crossed aldol reaction. So in order to help this reaction only produce one product, what we do is we use LDA at cold temperature. So we would first take a solution of this ketone, treat it with a much stronger base, right? And at cold temperatures. So it will form the enolate from the only component that can, because this is the only one in solution at this point. Then we can dropwise add in the other component, and it's a faster reaction for it to do the aldol addition reaction than to essentially exchange and form some enolate from this one. So this would be necessary because of this alpha position, right? We'll make a note of that. This is an alpha carbon, and it has like acidic hydrogens, right? And over here we have no alpha carbon. So that's why we have to use LDA in this case and not this case. So then we will end up with the crossed aldol product. Okay, looking at the next question. Fill in the missing reagents. Why is sodium ethoxide used as the best choice base for the first step? So the first step here is this is a Claisen condensation, right? So it has a name. And we use the matched alkoxide. So because this is an ethyl ester, right? That's why we want to use the sodium ethoxide, because if you use sodium hydroxide, right, or any other alkoxide like sodium methoxide, we would get hydrolysis of the ester to the carboxylic acid, right? Or we would get transesterification to another ester, which would complicate this reaction. So that's why we want to use sodium ethoxide. Right, so we'll make a little note here, right, that we want to, match the R group. So because this is an ethyl ester, we're going to choose sodium ethoxide. Okay, moving on then we need to figure out, okay, what sequence of reactions is going to produce this ketone. So what we're going to do is we need to add these carbon-based groups. We need to add an ethyl group and we need to add a propyl group, right? This goes away as CO2 later on. And this is the ketone that we see, right? The methyl ketone that is still in the product. So it shows us that we're going to add the ethyl group here, which means that we're going to add the propyl group first. And then the last step will be the hydrolysis of this ester and decarboxylation to get to the methyl ketone product. So first we're going to add in, again, we're going to match, right, the base. So continuing on with sodium ethoxide. And then we're going to add in, because we want 1, 2, 3. So we're going to add in 1, 2, 3, right, with a good leaving group. That will produce the product where we've alkylated the alpha position and added 3 carbons. We can do that again because there's still a hydrogen here that can be removed with the base. We can alkylate a second time. So we can add in 1, 2, 3 and 1, 2. And then we can decarboxylate with water and heat, right? That will convert the ester to a carboxylic acid, and the heat does a decarboxylation. So we lose this carbon as CO2, and then we just end up with the methyl ketone with the alkyl groups that we sequentially added in. Show how this can be made via a Michael reaction. Which is the Michael donor and which is the Michael acceptor used to make this compound? Right, so we are going to do the reaction and form this carbon-carbon bond, right? So this is the carbon-carbon bond made in this Michael reaction. So then that simplifies, right, to two components. We have this enolate, and it's doubly stabilized, right? So this is a good Michael donor. So doubly stabilized means that there's resonance stabilization of this anion up to both oxygens. And then we have the acceptor, which is an alpha beta unsaturated group with an electron withdrawing group, which is the ketone. So this is a good Michael acceptor. And of course, this one, we can think of this one as being produced from deprotonation, right, of the hydrogen here. So this is an acidic hydrogen, right, with a pKa of about 10. It's acidic because it's going to be a stabilized conjugate base, right? So if we treat this with a base, in this case, we don't have any esters, so we don't have to match the base to the ester. We can just use any base like sodium hydroxide. It will deprotonate this and form the Michael donor, which will then do a nucleophilic attack, right, to form that carbon-carbon bond to do the Michael reaction. Show how this could be prepared using a Stork-enamine synthesis. Explain why an enamine needs to be formed for this Michael reaction to be successful. Okay, so if we start with this ketone, you have to remember back to a previous chapter where we learned about enamines, right? But we can produce an enamine, such as this one, right? And then this one can do the Michael reaction, right? And again, we're forming this new carbon-carbon bond. So looking at what's here as the electron withdrawing group, we have the aldehyde, we have the carbon, and this will have been the double bond, right? We're making, this is the new carbon-carbon bond that gets made. And that produces, right, this product. Okay, so how do we make the enamine, right? Well, we treat the ketone with a secondary amine, such as this pyrrolidine. And typically we would need an acid catalyst, right? And sometimes people will even write minus water because we need to drive water out of the reaction to favor the equilibrium in this reaction. So why, like if we compare and contrast with the last one, why in this case did we not need to form an enamine, right? But in this one, we do have to form an enamine, right? So the simplest way is to think that this is the Michael acceptor, right? And this is a good Michael donor, right? And this is a poor Michael donor. And the problem is that if you treat this with a base and form an enolate, it's not stable enough, right? It's too reactive. Whereas this essentially is the same thing. It's nucleophilic at this carbon, but it's not as strong of a nucleophile. So it's much more stable, just like the previous case where we had the extra stabilization of the second carbonyl, right? So we can think of this as, right, a more stable nucleophile, right? If this had been deprotonated with sodium hydroxide, this is not stabilized enough, right? We can think of this as too reactive and too nucleophilic. And so then the problem is that it ends up not just doing the Michael reaction, but the nucleophilic carbon can also directly attack the aldehyde carbon or the ipso carbon. So it ends up giving a mixture of products. Right, so this is not a stable enough nucleophile. If there was a second carbonyl here, it would have been a stable enough nucleophile. But we need an additional electron withdrawing group, right, that this can help stabilize this, and we don't have it, right? But this is much weaker nucleophile, so it's much more stable. So it will do a successful Michael addition, right? But we call this the Stork-enamine synthesis because we're giving a lot of credit to the fact that we need to form an enamine for this to be a successful Michael reaction. All right, the next one says, draw an alcohol, carboxylic acid, ketone, and 1,3-diketone. Highlight the most acidic proton in each and state the approximate pKa value. Rank them from most acidic to least acidic. Okay, so let's go ahead and draw all of that out, right? So we're going to draw out an alcohol, and I'm going to go ahead and draw in the most acidic hydrogen, right, in red. So we have a carboxylic acid, right? I can draw it like this. Next, it wanted a ketone. So we can go, okay, how about something like this, right? Technically, there are 4 hydrogens in the alpha position, but I only need to draw in 1. And then a 1,3-diketone. So we're going to do 1,3-diketone. Again, there are 2 hydrogens at this carbon, but I only need to draw in 1. Oops. And I drew it in black, but I wanted it to be in red. So there you go. Sorry about that. Okay. And then it wants the pKa value, right? So this is going to take some remembering on our behalf. The pKa of an alcohol, right, is typically, let's say, about 17 or approximately, right? That's the most important thing, is just approximately here. Carboxylic acids, approximately 5, right? The alpha position to just 1 carbonyl, and we'll say the pKa is approximately sort of 19 to 20, right? We'll just go with, like, doesn't really matter which one you think here. Let's go with 20. And the pKa in between 2 carbonyls, approximately 10, right? So if I was to give all of these a letter value, right? We'll call this A, we'll call this one B, C, and D. So if we were doing a ranking, right, and we want to go from, it said from most acidic, right, to least acidic. So we want to remember that the most acidic ones will have the lower pKa. We want to go from lowest pKa to highest pKa here for the ranking. So then we are going to go with, okay, what's the lowest, right? The carboxylic acid. So we would do B, right? Next would be D, then A, and then C. Okay. Provide the IUPAC name for this amine. So we want the longest carbon chain that includes the carbon attached to the nitrogen. All right, so this is just one carbon. That's not going to be the longest carbon chain. It's clearly going to be up here. And we want to get to this with the lowest number possible, right? So we can think about possibly starting over here and getting to it, right, by carbon number 3, which is faster than if we had started here and worked our way in the other direction. Okay, so now we have we can think of it as, okay, what are our substituents, right? And then we can think, what is the parent, right? And then we want to also think about RS, right? So RS, so are there any stereocenters? And there definitely are 2 of those here. So we need to consider that as well. Okay, so moving in any order that you want to, right? We can think about these. So I'm going to work on the substituents first, right? So we have a 6-bromo. We have a 2-methyl, but the amine also has a methyl, right? So this is going to be a dimethyl, right? So we are going to go with N. So N comes before the number 2, dimethyl. And again, that's because N is used as the locant for this methyl group. And then we have the 2-methyl here, and the N always comes before any number. So it becomes N2-dimethyl. So those are our only substituents. Of course, we want to think about alphabetical order, right? B comes before M in the alphabet. So we're going to do the 6-bromo first. All right, what about the parent then? Well, we know that, right? It's 7 carbons. So 7 carbons, if it was an alkane, we would call it heptane. But in order to have an amine, oh no, I have to go back and fix a previous question. I just realized that I messed this up earlier. Okay, sorry. So this is not amine, it's amide, right? So we're going to end up with hexanamide here. Sorry about that. Okay, moving back to this one. This one is heptanamine. This is an actual amine and not an amide. Okay, and then because it's not carbon number 1, we do want to include that. So we can either call this a 3-heptanamine, right? Or we could do a heptan 3-amine. And the second way is the newer way that IUPAC has laid out for this process. Okay, for the chiral centers, right, we can sort of think of this one first, or it doesn't really matter which one that you do, right? But if I think about this one, sometimes people like to just sort of put the numbers in and then think of it from there, right? So bromine would be the first priority. Then we would have the hydrogen here, which would be the 4th priority. The 2 carbons are a tie, but this carbon is more substituted than this one. So this is priority 2, priority 3, right? So we can also switch these two because our 4th priority is coming out at us and not going back, right? We can do a switch. And if I switch those two and I switch those two, then whatever this is, R or S, the next thing that I draw will be the same thing. So this is just a strategy here. You can, if you do it a different way, that's totally fine. Right, so I'm going to switch those two. Now that I have the 4th priority in the back, it's easy to see the 1, 2, 3. Right, this is a counterclockwise rotation, so this means that's S. And because I switched 2 and switched another 2, right, this one will also be S and this one will be S, right? So this one is S. All right, so coming over here for the other one down here. So I'm going to draw it where the 2 lines that are in the plane are here. I've got my group coming out at me and I have a group that's not shown that's pointed back, right? And then I just need the 1, 2, 3, and 4, right? So I have the nitrogen, hydrogen, carbon, and carbon. So nitrogen is going to be priority 1. Hydrogen will be priority 4. And then these two are both carbon, so they're a tie. But this carbon is attached to carbon, carbon, hydrogen. And this one is carbon, hydrogen, hydrogen. So this has a higher priority. So this is actually 2 and this is 3. Checking this, I already have my 4th priority pointed back. So that's ideal. So I don't have to do any switching. So I can just do 1 to 2 to 3. Again, this is a counterclockwise rotation. So this one is also S. Right? So we can draw that in as well. They're both S. Right? So we can do in parentheses, and we'll do this by number, 3S, 6S. Okay, now we need to put it all together. We start with the stereochemistry. So 3S, 6S, and then we have 6 bromo, N2 dimethyl. And then we need the parent, right? So we can do heptan 3 amine. Okay, moving on to the next question. Rank this group of compounds in order of increasing boiling point. So let's do that. So we have we want to think of this as a primary alcohol, right? With maximum nitrogen-hydrogen bond. So it has the most hydrogen bonding because it has 2 nitrogen-hydrogen bonds, right? And this has the second most amount of hydrogen bonding possible with only 1 nitrogen-hydrogen bond, right? And this has no hydrogen bonding because there's 0 nitrogen-hydrogen bonds, right? So this is supposed to be 0, not O. Okay. So placing these in order, the ones with the most hydrogen bonding, right, will have the highest boiling point because it's going to take the most amount of energy to break apart those molecules and get the compound to boil. So increasing means we really want to start with the one that has the lowest boiling point and the least significant intermolecular forces, right? So A, B, C, by the way, they all have dipole-dipole and London dispersion. So the difference is really in the presence of hydrogen bonds and how many hydrogen bonds in this case. Okay, so if we are ranking in terms of increasing boiling point, right, going this direction, we want to rank B, then we're going to go with A, and then C. Okay. Provide the reagents and predict the product of the Hoffman elimination of the following substrate. Okay, so Hoffman elimination is an elimination to form the Hoffman alkene, which is the less substituted, less stable alkene, right? So if we're looking at this is the alpha carbon for amine, so it's the carbon attached to the nitrogen. If we're looking at the beta carbons, where we could possibly lose a proton, we want to lose one at this is at the least, right, substituted beta carbon. So then we're going to end up with the least substituted alkene, right? So this is the Hoffman alkene. And the reagents, in order to get there, right, we need 2 steps. The first step is to treat with excess methyl iodide. That's going to methylate this nitrogen 3 times, right? So we replace both hydrogens with a methyl, and then it even adds a 3rd methyl, right, to get to the ammonium ion. So this creates a good leaving group. And then we can treat with silver oxide, water, and heat, and that will give us the Hoffman elimination product. Provide the 2 reactants you would use to prepare the following azo dye using an azo coupling reaction. Indicate, or which of the indicated bonds should be made and why. So we actually want to make this bond, right? And not this one. And the reason why is because we want the ring that acts as the nucleophile to be the electron-rich ring, right? So this side is the electron-rich aromatic ring, because it's going to act as a nucleophile. In the EAS, electrophilic aromatic substitution reaction, that's needed to produce the azo dye. So this one is the more electron poor ring because it has a electron withdrawing group, right? Whereas this is an electron donating group and this is an electron donating group, right? So this one is the electron poor aromatic ring. And that would not make a good nucleophile for an EAS reaction. Okay. So not a good nucleophile. Okay, so then the 2 components we would want are, so if we're making this one, right, then that bond isn't going to exist. We're just going to draw in OH and then the other substituent here, right? And then on the other side, we're going to have the other aromatic ring. It's going to have the diazonium salt attached to it and whatever electron groups attached to the ring as well, right? So these are the ideal reactants. Okay. So this one is the fill in the blank section on the midterm. This is a guide to it. So we want to know the reagents, right, for all of these reactions. Okay, so to convert an acid chloride to a ketone, we can use a Gilman reagent. And because we want to add in a methyl group, right, that's where we're going to come up with the methyl Gilman reagent to do that. Again, if I had added an ethyl group, I would have added an ethyl Gilman reagent. This is a aldol condensation reaction, and maybe taking some notes here, right, would be helpful. So you could write in the names if there is a name for the reaction or something that will help you remember it, right? So this is a Gilman reagent, so that I'm not going to write it in, but it's optional as you're watching this video to, if that helps you remember, you could do that. So this is an aldol condensation reaction. So two components of this ketone will react together, right? And typically for an aldol condensation, we would use sodium hydroxide, and we also need to heat in order to get the alkene here, right, all the way to the condensation product. And then this is a conjugate addition reaction, right? Also known as a Michael reaction. So we're adding in this methyl group, right? And so that is going to be coming from the Michael donor, and then the double bond here, that's the alpha beta unsaturated ketone, that will be the good Michael acceptor. So we actually can do this Michael addition or this conjugate addition with the same Gilman reagent we used over here. And again, I'm adding methyl, so that's why I'm using the methyl Gilman. Okay, fill in the missing reagents. Okay, so we see that this is similar to what we saw, right, on the last one. So going from the acid chloride to the methyl ketone, again, we're going to use the same Gilman reagent. What about going from an acid chloride, right, to an amide? So we can add in 2 equivalents of ammonia because we're just adding NH2. Going from a primary amide to a nitrile uses SOCl2. And then going from a nitrile to a methyl ketone, we actually can use a Grignard reagent. So in this case, we want to add the methyl magnesium bromide. So with an acidic workup. And now we have alkylations, right? Because from this ketone, we have 2 alpha carbons, and we're either adding in a methyl, right, at the more substituted alpha carbon or the least substituted alpha carbon, right? So going from the more substituted one, we can use a small base, and the less substituted one, we want to use a bulky base, right? So in this case, for the alkylation, for the small base, we use sodium hydride, and typically at a room temperature or an elevated temperature. Sometimes they'll write 25 degrees Celsius, which basically means room temperature. That will form the most substituted, most stabilized enolate, right? And then we can add in our alkyl halide electrophile. We're just adding a methyl group, right? So we're going to add in methyl bromide. So I'll just write 25 degrees Celsius just in case, okay? Over here, we would want to use LDA at a very cold temperature. This is a much more bulky base, and it will selectively remove a proton from the less substituted carbon, forming the enolate on this side. So then when we add in the methyl bromide, it will add in on that less substituted carbon. Fill in the missing reagents and structures. Okay, so we might want to think back a little bit for this. How do we take an alkene, right, and form the Markovnikov hydrate product? So this is a Markovnikov hydration. We don't need to worry about rearrangement. So we can just use H3O plus, or alternatively, we could use the mercuric acetate conditions. Although it's not necessary in this case, because we don't have to worry about rearrangement of that carbocation. From here, it looks like we have three steps to get to this alpha beta unsaturated ketone, right? So if we target potentially making the ketone, then these conditions will brominate the alpha position, and the bromine will go on the more substituted carbon, right? And then we can, from this, we can use a base like pyridine, right, to eliminate that and form the alkene. And then this is an oxidation of a secondary alcohol to a ketone, right? So we could use PCC, or we could use the stronger oxidizing conditions. Would work for that as well. Okay, so this one actually I noticed is the same question as multiple choice question number 12. So I will just refer you to question number 12 from the multiple choice section to review this series of reactions. Fill in the missing reagents or structures. Okay, so we want to pay attention to the way these arrows are going so that we note that this is the starting material, right, for 3 different reactions here that we have to come up with reagents for. So as always, when you're looking to fill in reagents over arrows, take a note of which way the arrow is going, right, so that you can fill in the correct reagents. So I noticed with these two, we're forming amines, but this one has the same number of carbons, and this one has added a carbon, right? So that's the difference, right? If we're not trying to add a carbon, then we can use NaN3, which is sodium azide, and we can do a hydrogenation or use lithium aluminum hydride to reduce the azide to an amine. Because we do want to add a carbon here, we want to be careful to use sodium cyanide. So that actually adds a carbon. We get a nitrile intermediate, which can also be reduced under lithium aluminum hydride or a hydrogenation. Okay, and then going from this to the carboxylic acid, notice that we have added a carbon, right? So we want to do this because this is primary. We could do it either way. We can do, so we've looked at this reaction several times already. And form a Grignard reagent, add dry ice to add CO2, and then an acidic workup will provide the carboxylic acid. Or because this is a primary carbon, we also have the option to use sodium cyanide. This only works with unhindered alkyl halides because it does require an SN2 reaction. And we can do a hydrolysis of the resulting nitrile. Takes a lot of heat, right? But eventually you can get to the carboxylic acid. Okay, from here, it looks like we want to form an amine. Remember that carboxylic acids themselves are not super reactive, but they are there is a way to form something that is much more reactive from a carboxylic acid. We can target the acid chloride, right, through SOCl2. Now we have a much more reactive functional group, right? It can react with excess ammonia to form a primary amide. Some people call that an amide. And then we can reduce this carbonyl using LAH. All the way down to the primary amine. Okay, the next question. Show how you can make a tertiary amine through successive reductive amination, starting with an aldehyde. Okay, so basically we need to do multiple reductive aminations. So if I look and see here, I have an aldehyde with 1, 2, 3 carbons, right? So perhaps one of these groups with 1, 2, 3 will have come from the aldehyde. So we can do our first one and either add in this ethyl group, right? Ethylamine or propylamine. Let's go. I'm going to go ahead and add in the propylamine first. And then I'm going to target forming this one because I'm going to add in a propylamine. And it could have the opposite order where you added the ethylamine would have also been fine. And so these react together to form an imine, which is then reduced, right? So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So just be consistent with your carbons. So we do need a acid catalyst, right? And then we use sodium cyanoborohydride as the reducing agent in reductive aminations. So now we want to add in this last group here. Right now we have an amine, so we need to add in the aldehyde or ketone component. Because this is a primary carbon, we're going to end up using an aldehyde. So we're going to use a 2-carbon aldehyde. Same conditions, acid catalyst, sodium cyanoborohydride. That will form an imine here, right? Which will be reduced with the sodium cyanoborohydride. Okay. Show how you can form a, let's see. To focus. Show how you can form an aryl diazonium salt from aniline, and then list 7 reactions of aryl diazonium salts. Okay, so if we start from aniline, remember aniline is NH2 or an amine attached to an aromatic ring, right? So this is aniline. And we can form aryl diazonium salts from aniline. And that looks like this. And the conditions for that are NaNO2 and HCl. And then from here, it says 7 reactions of aryl diazonium salts. So these are lots of different options of things that you can make here, right? So we can form a phenol. From water and heat. Heat is sometimes just drawn as a triangle. And then we can replace it with a hydrogen to just make benzene here with H3PO2. And then we can also put on a fluorine using fluoroboric acid. Okay, and then we can also do the Sandmeyer reactions, of which I believe there are 4, right? So there's 1, 2, make sure I can fit everything from the same starting place, right? So we can put on 3 different halogens, chlorine, bromine, iodine, and a cyano group as the last one. Right, these are all called the Sandmeyer reactions because they use the copper reagents. So copper chloride, copper bromide, copper iodide, and copper cyanide. And then let me just look something up really quickly. I may have forgotten here. So I think I could have gotten one of the reagents wrong here. Oh yes, okay, that's what I thought. It's HBF4, sorry about that. Okay. Next is provide an example reaction for each of the named reactions below. Okay, so how about the aldol condensation? So for an aldol condensation, we usually take an aldehyde or a ketone, right? And we would end up using 2 of these, right? We would use sodium hydroxide and heat. And we would go all the way to the alpha beta unsaturated carbonyl containing component, right? So 1, 2, 3, 4, because we're using 2 of these. 1, 2, 3, 4. So always double check your carbons there. Okay, how about a Robinson annulation? So a Robinson annulation is 2 things, right? You first start off with a Michael addition followed by an aldol condensation. So it's those 2 things together. I'm just going to use a different color just so that it separates in your mind, hopefully. And so we start off with a good Michael donor, and we use a Michael acceptor, something like this, right? And then the conditions would be sodium hydroxide and heat, because again, we are going to, it first starts off with a Michael addition and then does the aldol condensation, right? So we need the heat in order to go all the way to the condensation product. So that is actually going to form a bicyclic product, right? This methyl is still there. One of the carbonyls is still there. The other one, think of it as converting into an alkene, right? And then this carbonyl is this one, right? And this double bond came from this. It's no longer there. Okay, so let's think about the Fischer esterification. So in a Fischer esterification, we have 2 components, right? We have some sort of carboxylic acid, and we have some sort of alcohol. right? And they require a strong acid catalyst to form an ester. Okay, let's look at the next one, which says, give an example of a Claisen condensation. Well, sort of standard example here for a Claisen would be like an ethyl ester, right, with just 2 carbons here. This is going to dimerize, so 2 of these will react, sort of similar to the aldol. And the product will be a beta keto ester. So this ester will be there and we'll add in a ketone. So we're going to be losing one of our esters, right? So then essentially this gets added on to the first, right, to get a beta keto ester. And the conditions for that are we need excess NaOET. Remember, we want to match the base to the ester. And then the second step is we are going to need an acidic workup in order to reprotonate the hydrogen here that's acidic and gets removed during the reaction. Okay, moving on to the stork-enamine synthesis, right? So we have a, we want to start with some sort of unstabilized, so only 1 carbonyl ketone, because we are going to be doing like a Michael reaction, but we're going to do it with an unstabilized ketone. Right, so simple example would be maybe just like acetone, right? Just a very simple ketone here. And we are going to first form an enamine. So we're going to treat that ketone with a secondary amine, right? With a strong acid catalyst. Lose water, so we'll form the enamine in that step. And then we want to add in some sort of alkene with an electron withdrawing group, right? It could be anything. It could be a carbonyl from an aldehyde, ketone, ester. It could be a nitro group. That's another electron withdrawing group. So that's the example I'm going to use here. And then we typically need an acidic workup. And we will form, we would have formed the enamine, but the enamine goes away eventually. And it's going to form a bond with this carbon, right? So we're going to attach this to carbon, carbon, and then nitro group. So carbon, carbon, and then nitro group. Okay, the Dieckmann cyclization. Okay, so the Dieckmann cyclization is an intramolecular Claisen condensation. So we can start off with something that has 2 esters in it. And we want to form a decent sized ring, right? We want to form a 5 or a 6 or a 7 membered ring because those are all stable sized rings. And so they're fairly easy to form. So we want to make sure we have the right number of carbons here. So always remember that if you have 4, a bridge 1, 2, 3, 4 in between your esters, you'll end up with a 5-membered ring because one of the carbons from the carbonyl is also incorporated into the ring. Right, so this will end up giving me a 5-membered ring, right, with a ketone here, and I'll end up with an ester. So again, it's like, think of it as like in Claisen because you end up with a beta keto ester, but it occurred intramolecularly, and then it's called a Dieckmann cyclization. So the reagents for this are still excess NaOET, so similar to the Claisen condensation above, right? And we want to match the base. And then we are going to do our same thing we saw above, H3O plus workup. Okay, what about the Gabriel reaction? So that one, it was a way to produce primary amines. And it starts off with potassium phthalimide. This is from the amine chapter. Right, so this is an aromatic ring. And we'll just start here and produce the potassium phthalimide through deprotonation with potassium hydroxide. We're going to use some sort of alkyl bromide, right? Maybe like 3 carbons. And then we're going to either use H3O plus or hydrazine. So NH2, NH2, so that hydrazine, I guess I could have written the hydrogen on this side, NH2. Or again, H3O plus would work here. And we would end up with the 1, 2, 3, 1, 2, 3, and then draw in a NH2. Right, so most of these atoms are actually byproduct, end up in the byproduct. Only the nitrogen gets transferred in this reaction. And then the last reaction is the haloform reaction. And the haloform reaction produces a carboxylic acid from a methyl ketone. Right, so we take our methyl ketone, and usually this other side is fully substituted, so there's no alpha hydrogens here. That makes the reaction work much more cleanly. And again, we're going to get the carboxylic acid. So we've essentially done a carbon-carbon bond cleavage here, right? And then we typically get a byproduct of, depending on what we use here, right? The halogen will match here. And a common example would be with iodine, just because iodoform is actually a yellow precipitate. So this is actually a test reaction for the presence of methyl ketones. So if we were going to form iodoform, you could also form bromoform or chloroform. Then we would use sodium hydroxide and iodine, right? And we can switch this out for like bromine if there was bromine here. And then we need an acidic workup, right? Because we want to have the protonated, isolated, protonated carboxylic acid. So we need an acidic workup to add that last proton. All right, so those are name reactions you should be familiar with. Okay, I am actually going to take a break here and come back in just a little bit. So we're going to, let's see, pause recording.